Hi everyone, my name is Raúl Gracia, and I'm going to give this talk entitled Crystal, Open and Extensible Software-Defined Storage for OpenStack Swift. So I'm a postdoc at Universitat Rovira i Virgili, and I'm also technical coordinator of the IFTTT project. The project is a software-defined storage for big data, and it's a 3.3 million euro European project. Basically, we are building a software stack for big data via software-defined storage models, and it is made up of 8 partners, including academics and companies. This work has been done partially with IBM, but there are, of course, other organizations in the consortium. So this talk is about software-defined storage for object storage. So first of all, what is software-defined storage? So there is not a consensus about this term, but we can say, roughly speaking, that it's a way of managing a storage system in which the resources, the storage resources, which is the data plane, are independently managed from the control plane. So administrators can write storage policies in order to manage the underlying storage systems via provisioning services and so on in a simple manner. According to Gartner, software-defined storage is powerful. It can reduce the cost of managing large clusters. It provides flexibility and agility for companies. And it can also help to optimize performance in specific workloads. And our focus in this case is object storage, so OpenStack Swift. What has been done so far? So recently, Swift has adopted the term of the idea of storage policies, which helps basically administrators to define in software different types of redundancy models, including replication, coding, and so on. And there are also industrial advances in this aspect. For example, SwiftStack is a company that is bringing Swift to the next level, providing automation, metering, and provisioning services on top of OpenStack Swift. But my question is, can we go a step further? And if so, why? So let me show a couple of data advanced storage management problems. Let's imagine 2 tenants, okay, that are basically storing data in Swift. Tenant 1 stores compressible data, tenant 2 stores uncompressible data. So my question here is, can we compress only T1's data to save storage space? So the answer is that not easily in Swift. But let's go for a more dynamic example. We have, again, 2 tenants, and we want to guarantee a minimum bandwidth of 30 megabytes per second to tenant 1 and 60 megabytes per second to tenant 2. So the question is, can we dynamically execute some filter that dynamically ensures a bandwidth of 30 megabytes and 60 megabytes to these tenants? The answer is, again, not easily in Swift. So the solution to these problems is Crystal. What is Crystal? So Crystal is the first open, extensible, and programmable SDS architecture for Swift. Okay? You can visit the web page and also go to the GitHub repository. So let me explain the concepts behind Crystal. So Crystal is a framework to solve storage management problems in Swift. So it is not a particular solution to a specific problem. Okay? So following the guidelines of software-defined storage, at the data plane, we find filters and metrics in Crystal. And then in the control plane, we find policies and controllers. I'm going to explain these concepts now. A filter can be thought as a piece of code that executes a data transformation on object request. And this concept is broad enough to encompass data compression, caching, encryption, and many other types of filters. So basically, you have a user and the storage system. So when a new put gets into the system, for example, the storage filter intercepts the request, executes compression in this case, and it is transparently executed for Swift. Crystal provides a filter framework that enables developers to deploy arbitrary code that will be transparently executed in Swift. At the moment, we provide filters via OpenStack storelets. They provide a nice Dockerized way of executing filters, and also a native filter platform to execute filters in a more flexible manner, more complex filters, actually. Filters are pluggable and deployable at runtime. On the other hand, we have the concept of metric, which is basically an information source about the workload at hand or a particular aspect of the system. So we can think about bandwidth, metrics, requests per seconds, and so on. So Crystal also provides a metrics framework that enables developers to deploy arbitrary metrics to capture some aspects of the system operation at runtime. And they are also pluggable and deployable at runtime. At the control plane, we have the abstraction of controller, which is basically a controller is an algorithm that receives information from workload metrics, execute some intelligence, and then orchestrate the behavior of a storage system, of the storage filters. So, and last but not least, we also provide a nice DSL that administrators can use to change the behavior of the system. For example, we can see administrators can write policies such as, for container C1, when the number of gets per second is larger than 5 and the size of the object is smaller than 10 megabytes, then execute caching on this request. This is only a simple example of what administrators can do with Crystal. Let's see a simple example of how it works. So let's see that, imagine that we want to define this policy for tenant T1 to set compression. So the first entity that comes into play is the filter framework that is installed in the cluster but does not modify the code of Swift. And then first of all, because we need to enforce a compression filter, the administrator installs the compression filter via the API, and it is readily available in the storage cluster. Then the policy is submitted to the system, and the DSL compiler interacts with the API, and then the API stores the metadata store that compression should be enforced on tenant 1's request. Then, when tenant 1 stores a new object in the system, Crystal realizes that it has to enforce compression on this particular request, and transparently, the data is compressed and stored in the system. All of this life cycle can be easily managed via a dashboard that we provide. For example, the management of filters, the management of metrics, and also the definition of policies. And this is integrated in OpenStack Horizon. Let me show a more dynamic demo. So here we have two workloads that are reading data from Swift, okay? And now we can throttle the, okay, it's not working. I'm sorry, the video seems not to work.
Yeah. It should just be, click on the video, it should play.
No?
Let's go back a slide. We might just have to live without it.
Okay. Okay, so in this demo, I basically was going to show that we can enforce bandwidth SLOs for different tenants. So there was some problem with the video, unfortunately. So Crystal, in fact, is being applied in the context of the IOStack project on several use cases. For example, GridPocket is a smart grid energy company. So one of the things that this work was done in conjunction with IBM, and one of the things that Crystal helps to do is to make Spark SQL queries much faster than for GridPocket. In this case, up to 30 times faster. And why? Because in conjunction with IBM, we developed storage filters in Swift that can execute SQL projections and selections to discard useless data on the storage nodes. So this makes the Spark cluster to execute queries much faster because the ingestion phase of data is reduced heavily. For example, here you can see some query speed up numbers that go from more than 20 to up to 37. And this experiment has been done in the OpenStack Innovation Center. But there are other use cases that benefit from Crystal. For example, Idiada is an automotive company. Crystal is providing in a pilot deployment of Swift, storage savings via compression techniques and also data privacy. And this is done thanks to the deployment of compression filters and encryption filters to store car standardization documents. Or for example, we have also another use case, Artur, which is an Slovenian data center and hosting solutions. So basically, Crystal is helping Artur to manage the performance of web applications in multi-tenant Swift clusters. So they are executing bandwidth differentiation filters and caching filter to differentiate the different performance of web applications. So this is, that's it, the talk, and thank you. Please join our community and visit our webpage. Thank you very much.